So this video will be a general overview about how to calculate the singular value decomposition of a matrix. So if you have a matrix A and you want to write it in the form U sigma V transpose, where U and V are orthonormal matrices, that means that the vectors inside are orthogonal to each other and all vectors have length 1, so they are normalized. And sigma will contain the singular values. So first, a bit of intuition. Where does this strange formula come from? Well, if U and V are orthonormal, that we can consider them as a set of bases of our vector space, if you want. So, for example, if you are in 2 dimensions, you would have 2 vectors for V, V1 and V2, and they would, if they are orthonormal to each other, and you are in 2 dimensions, so you have 2 vectors of them, they could span our vector spaces or dimensions if you want, and so that they would be considered as a basis of our dimensions. And the same thing is true for U. If we are like in 2 dimensions again, if both vectors are orthogonal to each other and are of length 1, so they are orthonormal, we can see them as a basis of our vector space, if you want. And now the main concept of the singular value decomposition is that if you have a matrix, some random matrix A, and you apply it to a vector X, it does 2 things. It rotates the vector and it stretches it. So stretch it by a positive or negative value, a value greater than 1 or between 0 and 1, whatever. So it does 2 things. It does a rotation in some directions, and it stretches the vector by some amount. It can do both or only one of both, but it can do both at the same time. And the whole concept of the singular value decomposition is that if we know that if we apply our matrix A to our vector X, we get some rotation and some stretching, we can say that it's the same thing as if we have some other basis, some vector in another basis, U, and we stretch those basis vector each by some amount to get the same thing as our our matrix A. And our vector X is at the beginning already written in some basis, V, if you want. So like I hope it's clear what I want to say. It's like suppose that V1 and V2, suppose we are in 2 dimensions, and V1 and V2 are our bases, so basically our X vector and our Y vector. And now we have some vector X, let's see like that one maybe, and we apply our matrix A to it, so it will rotate our vector and stretch it. So suppose that after that we get like something like that, if you want. We can say that this is the same thing as if you have our set of basis vector U, so U1 and U2, and then we stretch each of this vector by some amount to get our rotation and stretching of the vector X, if you want. Okay, so like if you want to get this vector here, we could like take, I don't know, 2 times this vector here, and then maybe negative 0.1 times this vector here, so that we are here, and so that we get the same vector as here. Okay, so that is the whole concept. Basically, you have some basis V, and you have some vector X in this basis V. Then you apply your matrix A. You do 2 things: you rotate and stretch the vector. You can of course also only rotate or stretch, because you could do both at the same time. And we say that it is the same thing as if you have some basis that will basically deal with our rotation. So basically we have a rotated basis U, and then we stretch all the vectors of this rotated basis by some amount, sigma 1, sigma 2, and so on. And so we get basically what our matrix A does. And so if you know, I said that AXV is equal to U sigma. If we know that U and V are orthonormal, they need to be orthonormal to be a basis. We know that V transpose is equal to its inverse, and so we can write that AX is equal to U sigma V transpose X. There should be a vector X, of course, because we are dealing with a vector on both sides. And so we know that A is equal to U sigma V transpose. I hope it makes a bit of sense. Yes, and I hope you can still read what I am saying. Yes, so we found out that we can express the rotation and the stretching of our that our matrix A does to a vector by some rotated basis u and some stretching factor sigma. And yes, our vector or matrix V, is the original basis. Yes. Yes. So our matrix V will contain a set of n orthogonal vectors that are of length 1. So the matrix will be orthonormal. So here I said in 2 dimensions. You cannot read it, I know, but still, we would have 2 vectors and each of length 1. Yes, our vector x will have n components if you are in n dimensions. Our vector u will again have n vectors if you are in n dimensions, and will be a basis, the rotated basis of this this vector space. These dimensions. And our matrix sigma will contain the stretching factors, if you want, that we will apply to each of the vector of this rotated basis. Like u1 will be stretched by sigma 1, u2 by another amount, and so on. Yes, and yes, before I forget it, if we create our matrix sigma, generally we place the sigmas in the matrix in such a way that sigma 1 is greater than sigma 2, which is greater than sigma 3, and so on, until we get to sigma n. We do this so that the strongest value is at the beginning and the lowest at the end. And we will arrange our vectors u, u1, un so that they match accordingly. Like so, if we put the strongest value of sigma 1 here, we will put the eigenvector associated to this sigma 1 in the first place. If you put the sigma 2 here, so the second strongest value, we will put the eigenvector associated to this sigma 2 in the second place. Yes. Yes. The singular values sigma can be found by first finding the eigenvalues of A times A transpose or A transpose A, and those eigenvalues will be equal to the square of those singular values. So like if you find like lambda 1 is equal to 4, we know that's equal to the square of sigma sub 1. So sigma sub 1 would be in this case equal to 2, because sigma 1 squared will be 4, and it will be your eigenvalue. Yes. So now, why is it so? Why do we need to find the eigenvalues of A times A transpose or A transpose times A? Well, if you have our singular value decomposition, A is equal to U sigma V transpose, we can write A times A transpose as U sigma V transpose, so that is A times U times sigma transpose times U transpose. Okay, so that is A transpose. Okay, I just transposed this thing here. That's U sigma V transpose transpose. If you transpose that, you get that. Yes. Now, remember, V and U are orthonormal. So here we have U transpose times U. This is a U here. This is this is a V here, and this is a V here. So we have V transpose times V, and so the product of both will give us the identity matrix. Okay, because remember, the transpose of a orthonormal matrix or orthonormal matrix, is equal to its inverse. And so if you multiply a orthonormal matrix by its transpose, we get the identity matrix. Yeah. So at the end, you are left with U times sigma transpose times U transpose. Yes. And now we can take the U transpose on the other side, so we can multiply by U on the right, and you get that A times A transpose U is equal to U times sigma transpose. And so now remember that our matrix U is just filled with an n amount of vectors U that are the basis of our rotated, that together form our rotated basis, if you want. Remember, our vector U, our matrix U is just filled in with n vectors U. Okay, our matrix U is just filled in with n vectors U. And yes, so we know that A times A transpose times one of this vector U between 1 and n, so I with index I, that is equal to this vector U times the singular value at the ith index squared. Okay, that is squared because we have sigma times sigma transpose. I hope you can figure that out. If you if you compute it, if you do sigma times sigma transpose, you will get sigma 1 times sigma 1, sigma 2 times sigma 2, and so on. And so for the ith element, so between 1 and n, yes, we get sigma sub I squared. Okay, I really hope you understand what I mean. You have that A times A transpose. If we compute that using this representation, U sigma V transpose, we get that A times A transpose is equal to U times sigma sigma transpose U transpose. And so A times A transpose U, if you multiply by U on the right, remember that U is orthonormal, so its inverse is its transpose, we get that this is equal to U times sigma sigma transpose. And so now remembering that U is just a matrix filled in with n vectors U, we know that A times A transpose times U sub I, so I is between 1 and n, is equal to S sigma sub 1 squared, okay, because we have S sigma times sigma transpose times U sub I. Yes, and so if you notice, this is our vector U sub I here too, and here we apply a matrix to it simply because A times A transpose is again a matrix, and we say that this matrix A times A transpose applied to our vector U sub I, that's equal to sigma sub I squared times U sub Y. So we can conclude, if you remember the definition of the eigenvalues, we can conclude that sigma sub I squared should be equal to our eigenvalue. Okay, lambda sub I is equal to sigma sub I squared. Yes, and that's why the singular value of our matrix squared are equal to the eigenvalues of A times A transpose. And we can do the same thing with A transpose A. We can write it as V sigma transpose sigma V transpose. Okay, here in the middle we should have U times U transpose. If you just compute it, I mean, you can write that U sigma V transpose that is equal to V times sigma transpose U transpose, and then you have the A normal, so U times sigma times V transpose. So you would have like if you let me write it, you would have that A transpose A is equal to V sigma transpose U transpose sigma V transpose. Yes. And so again, remembering that U is orthonormal as we did with V here, both are orthonormal, so this is equal to the identity matrix, so we are left with V times sigma transpose times sigma times V transpose. Yes, and now again we do the same thing, we multiply by V on the right, so we get that A transpose A is equal to V, is A transpose A times V is equal to sigma transpose sigma V, and so again that the ith V vector, so the ith vector in the matrix V times A transpose A is equal to sigma sub I squared times V sub 1. So again we have that A transpose A applied to our vector V sub 1 is equal to V sub 1 multiplied by sigma sub I V sub I multiplied by sigma sub I squared. So again we can conclude that the singular value sigma sub I squared is equal to lambda sub I. So that's where this definition comes from. That's why we can find out, we can take the eigenvalues of A transpose A or A times A transpose and then find the singular values using that method. That it just comes from this mathematical proof. Yes. Now there is so how will you proceed in general? You will calculate A times A transpose or A transpose A. Depending on which is easier. Generally the one that results in a smaller matrix will be easier to compute. Like if you do maybe A transpose A, you will get a 2x2 matrix, but if you do A times A transpose, so the opposite, you will get the 3x3 matrix. So it's better to compute the 2x2 matrix because it's easier to find the eigenvalues in. Remember, because all eigenvalues, the eigenvalues of both cases are the same, so it doesn't matter. If one of both cases gives us extra eigenvalues, if you want, like if you have a 2x2 matrix and a 3x3 matrix, the 3x3 matrix could have an extra eigenvalue. That can happen, that happens generally, but in those cases the extra eigenvalues are simply 0. Okay, so again the we have the same eigenvalues, the same non-zero eigenvalues, and if one of the matrices has extra eigenvalues, those are simply equal to 0. That's important to remember. Yes. So what you will do is you will compute, as said, your A transpose A or A transpose. Then you will find the eigenvalues associated to this matrix. And using that fact, if you compute A times A transpose and find the eigenvalues, you will then find your vectors U. And if you compute A transpose A, you will find your vectors V. Yes, let me write it. If you compute A transpose and then find the eigenvalues lambda sub I, you will then find your eigenvectors U sub I. And if you compute A transpose A and find the eigenvalues, which are said the same if they are non-zero, you will find the eigenvectors V sub I. Okay. And so once you have found the vectors of your matrix U or V, you can use a simple formula to find the vectors of the other matrix. So if you have found the vectors of the matrix U, you can simply find some of the vectors of the matrix V and vice versa. So you can simply use the formulas that U sub I is equal to 1 over sigma sub I times A times V sub I. And V sub I is equal to 1 over sigma sub I times A transpose times U sub I. Again, where those formulas come from, if you have A is equal to U sigma V transpose, we have that A times V is equal to U sigma. Okay, we just multiply by V on the right. So we know that, remembering that V and U are just a bunch of address matrices filled with a bunch of vectors V sub I or U sub I, which are, as said, the corresponding eigenvectors of the eigenvalues. Sorry. We can see that A times V sub I is equal to U sub I times sigma sub I. Okay, for some vector V sub I and U sub I, where I is between 1 and n, because remembering that V and U have n vectors inside if you are in n dimensions. Yes, so we have that A times V sub I is equal to U sub I times sigma sub I, which is equal to sigma sub I times U sub I, because sigma sub I is simply a scalar, so you can multiply. Simply multiply your vectors U sub I. And so now, yes, we can divide by sigma sub I, because sigma sub I is just a set of scalar. So we have that U sub I is equal to 1 over sigma sub I times A times V sub I. And of course, the singular value cannot be 0. So again, this only works for the non-zero singular values or the non-zero eigenvalues. For the remaining ones, we will see it later. Yes, and the same thing for the other formula. How do you prove it? We know that A transpose is equal to V times sigma transpose times U transpose. Okay, we just transpose the whole thing. So we know that A transpose U, so again you multiply by U this time on the right side, is equal to V times sigma transpose. So A transpose U times U sub I is equal to sigma sub I times V sub I. And so again, if we want to find our V sub I, we can divide by sigma sub I. So V sub I is equal to 1 over sigma sub I times A transpose times U sub I. And again, the singular values and thus the eigenvalues, because remembering that lambda is equal to sigma sub I squared, should not be 0. Yes. Yes. How do you find your extra vectors if if you have 0 eigenvalue or, as said, 0 singular value? What you simply do is you need to find how do you say, you simply need to find a vector that is orthogonal to the other vectors in your matrix U respectively V, and then you need to normalize it. Okay, by that I mean that you remember that U and V are orthonormal matrices, so they are of all vectors inside are of length 1, and they are all orthogonal to each other. So what you need to do is you need to you just need to find a vector that is orthogonal to all other vectors that you found already, and then you just need to normalize it. So if you are in 3 dimensions, for example, and you have already found 2 of your vectors and you need to find the third one, you can simply use the cross product, because remember that in 3 dimensions the cross product gives you a vector that is orthogonal to the 2 others, and then you can simply normalize it if you need it, so just divide by its length. But of course, if you have already found the 2 other vectors and they are already normalized, you don't need to do that, because yes, if you take the cross product of 2 unit vector, you get a third unit vector. Okay, and if you are in other dimensions, you can, for example, use Gram-Schmidt or whatever. If you are in 2 dimensions, you can remember that if you have some vectors a, b, a vector that is orthogonal to it is simply you switch a and b, so you have the vector b, a, and then you add a minus sign in front of b or in front of a. And that is your orthogonal vectors. You can remember that for 2 dimensions. And otherwise, I said you can use Gram-Schmidt or whatever. You just need a vector that is orthogonal to the other vectors, and then you need to normalize it. Yes. Now, if you have your matrix A and it's an m by n matrix, so it has m rows and n columns. Suppose that if m is smaller than n, so there are less rows and columns. In this case, the matrix sigma that has the singular values inside is always of the same size as your matrix A. So yes, if A is an m by n matrix, your matrix sigma will also be an m by n matrix. And so in this case, if I said you don't have a square matrix, so you have either more or less rows and columns, you simply put your singular values that you found using the eigenvalues before. You just put them inside, and in the remaining columns or rows, you just put a bunch of 0. Okay, so I said if you have more columns than rows, so you have less rows than columns, you will simply put zeros in the remaining columns. And if you have more rows and columns, you will simply put zeros, a bunch of 0 in the remaining rows. Okay. And just remember, I said that your singular values, you should put them in descendant order. So the biggest singular value should be put first in the sigma matrix, and then the second biggest, and so on until the last one. Yes, and yeah, of course I said if you have 0 singular values, because you have 0 eigenvalues, you should put them at the end. Yes, I hope I have covered everything. Yes, so I said maybe just a quick review. So there is we want to decompose A into U sigma V transpose, where U and V are orthonormal. And the main idea is that we know that our matrix A applied to a vector, it does 2 things. It rotates and stretches a vector. So we can imagine that if you have some base V and the vector X inside and we apply A, it's the same thing as we have some rotated basis U, and we stretch the basis vector of this matrix U by some amount, negative, positive, greater than 1, or between 0 and 1, or whatever. Yes, and then what we do is we have done some mathematical proof to show that we can find the eigenvalues of A times A transpose or A transpose A, and use those eigenvalues to find our singular values, which will fill in our matrix sigma. And then we can use those eigenvalues to find the vectors that are inside the matrix U and V, because the vectors inside the matrix U and V are simply the eigenvectors associated to those eigenvalues. Yes. So if you compute A times A transpose, you will get and then find the eigenvalues. You can then find the eigenvectors U sub I, and if you compute A transpose A, you can find the eigenvectors V sub I. Okay, yes, and then you can use the formulas to quickly find the other eigenvectors. So if you have found the vectors V, you can quickly find the vectors U. If you have found the vectors U, you can quickly find the vectors V by using the formula that U sub I is equal to 1 over sigma sub I times A times V sub I, and V sub I is equal to 1 over sigma sub I times A transpose times U sub I. And again, remembering that the sigma should not be 0, because otherwise you divide by 0, and you cannot do that. And so if you have a singular value or several singular values that are 0, you simply need to find find the remaining vectors u or v. You should simply find vectors that are orthogonal to all the other vectors you have already found and should be normalized to length 1. So I said in 3 dimensions you can use the cross product and then normalize the result if needed. In 2 dimensions you can do the trick as we saw here. So yeah, you invert the coordinates and then you put a negative sign in front of one of both. And otherwise you can, for example, use Gram-Schmidt if you want. I hope you have heard of Gram-Schmidt. Otherwise look it up. Or otherwise maybe there are other methods, but I don't know right now. Yes. And I said the matrix sigma has the same number of dimensions as our original matrix A, and so if you have more columns or rows that remains at the end, we simply put a bunch of 0 inside, and the singular values are in the diagonal of the matrix, ignoring those extra columns or 0. Okay, and they are not they are ranked from the biggest value to the smallest value. Yes, and yes, our matrix U will be a m by n matrix. So if m is the amount of rows of the matrix A, and our matrix V will be a n by n matrix, so n will be the amount of columns of A. Yes, that's also important to remember. So U is a n by n matrix, where m is the number of rows of A, and V is a n by n matrix, where n is the number of columns of A. Yes, and so of course if you transpose V, because we have A is equal to U sigma V transpose, it won't change the dimensions because it will still be a n by n matrix because it is a square matrix. So if you take this transpose of a square matrix, you have still the same number of dimensions. Yes. Yes, I hope I forgot nothing. Yes, so those are the main ideas. So generally, how do you proceed? You find the eigenvalues of A times A transpose or A transpose A. You find the eigenvectors, which will be your U sub I if you calculate A times A transpose, and your V sub I if you calculate A transpose A. And then you use those formulas here, as we saw, to find the other vectors. If you find the vectors U, you find the vector V. If you find the vector V, you find the vectors U. And then, yeah, you fill in your values. And yes, you remember that the singular values are the square root of the eigenvalues that you found. And yes, you fill in your matrices U and V and your matrix sigma, and you have your singular value decomposition. Yes, so yes, I hope I forgot nothing. Yes, and that's it. Yes, thanks for watching.